Hello everybody. In this video I'll be working the kinetics problems for you that we had in discussion section. I know I already worked half of them already in discussion for you, but I figure why not make a video of all of the questions so that you can use them to study for the exam. This first question is pretty simple. It's asking about the figure at the right where A is disappearing over a time interval of 20 to 40 seconds. It's asking what the average rate is in that time period, right? So since it's asking for the time period between 20 to 40 seconds, all we care about are these two flasks right here, right? Remember then that the average rate equals the change in the concentration of A over the change in time. So simply, all you have to do, and we always do final minus initial here, right? At the very top of the fraction, we use the concentration of A at the 40 second time interval, which is 0.30 molar, minus the concentration of A at the beginning of the time interval of 20 seconds, which is 0.54, right, moles. And then all that is over the change in time. And again, so it's final minus initial, so 40 seconds minus 20 seconds. And if you do that math, subtract point zero subtract 0.54 minus 0.30, and then divide that by, it would be 20 seconds here at the bottom because 40 minus 20 is 20 seconds, right? And that will actually give you a negative number because the top is a negative number. But the thing is that we know for a fact that rates, unless we're in physics, are always positive, right? And so the answer you should come out with then is 1.2 times 10 to the negative 2 molar per second. And sorry about that, these should all be mole, not molar, because the unit given here in the figure is mole. Okay? Cool. Let's go to the next one now. So in this particular question, right, we had a slide actually in our notes that specifically taught us what it was to be an instantaneous rate, or how to calculate an instantaneous rate, right? And luckily enough, here we have this box too in the graph that tells you that the instantaneous rate at time t is equal to the slope of the tangent of the line at time t, right? So the question says calculate the instantaneous rate of the disappearance of, I think I said it was pentyl chloride, maybe, at time 0, right? So all we need to remember here is that we need to determine what the slope is, because the slope tells you what the instantaneous rate is, right? And it's the slope of the tangent of the line that's on the graph, right? So they've already given us some help here by giving us this dotted line to show a tangent right here. You could do a tangent on the other line as well, but we should probably do the tangent of the line closest to the time 0 since it's asking for time 0, right? And so it's pretty easy. If you remember then, rate equals the change in the C5H9Cl over the change in time. But in this case, we're looking for the slope, because it says right here the slope of the tangent gives us the rate, right? So the rate then equals the slope, which the slope equation is y2 minus y1 equals x2 over x1. Or I mean minus x1, right? So look at your graph here, and here you are at time 0, okay? And at time 0, you have a concentration of 0.1. So that can be one set of your coordinates that you'll use in your slope equation, right? And then the next one you'll just have to kind of like the next one you'll have to just kind of estimate, right? But if you go over here, I'm just going to use the end of this line here, and then the end of this line is going to be at 0.060. You could pick anything, right? But I'm going to pick the 0.060 because it's the end of the line. You could have picked 0.07 if you want to, but let's just put 0.060, 0.060, and the line actually does extend just a little bit past 200, a tiny bit past 200. And so then that means that your x here will be, or your time here will be approximately 210 for that x, and 0.060 for the y. So then the rate equals your ending y2, and we're going in a downward direction here. That's why it's we're going with that being the ending, right? And so 0.060 molar minus then the first y, which is that 100 right there, or 0.100, 0.100 molar, all that divided by 210 seconds from here, which is our final time, minus 0. So all you have to do is subtract 0.060 minus 0.1 minus 0.100 and divide that by 210. So you get the rate. Again, it should be positive. Okay. 1.9 times 10 to the negative 4 molar per second. So that's how you solve that one. Pretty simple. Pretty simple. Okay, so let's go to the next one. Here the question is asking, how is the rate of ozone disappearing? Oh, how is the rate at which ozone disappears related to the rate at which oxygen appears in the reaction of 2O3 becomes 3O2? And if the rate of O2 is and if the rate at which O2 appears is this rate right here, at this particular instant, at what rate is O3 disappearing at the same rate? Okay, so this is pretty easy because I've actually already given you a balanced chemical equation here, and you'll need that. Okay, and if you remember from the slides, from our notes, right? Again, the rate equals the loss, right, in the change of O3 over the change in time, right? But we're not exactly finished with that yet. And the reason why we're not finished with that yet is because we have a coefficient of 2 in front of the O3, which means it's actually a loss of 1/2 times the loss, 1/2 times the change in concentration, negative concentration of O3, right? And then that also equals the gain, right, of O2. So again, we have the change in O2 over time, change in time. But again, we have a balanced chemical equation here that we need to take note of. And since it's a 3, that 3 becomes a fraction, and now it's 1/3. Okay. So all we need to do now is solve for this, which is the rate at which O3 disappears. The rate at which O3 disappears. Okay, so how do we do that? Well, all we have to do then is set it equal to something that we already know. And we already know right here, given right there, that O2 appears at a rate of 6.0 times 10 to the negative 5 molar per second, right? So essentially, you could put this right here into this term right here, because they equal that. That equals that, right? Because this is a change in O2 right here, change in O2 over time. And the problem tells you that the change in O2 over time is 6.0 times 10 to the negative 5 molar per second. So what your equation becomes then is negative 1/2 change in O3, which is still the loss in O3, right? Disappearance of O3 equals oh, and I apologize, I shouldn't have put that parentheses there. It should go here, okay? In fact, I'll erase that real quick. So there's no confusion. There we go. Okay, so the 1/3 stays, right? It's actually this part right here that gets replaced with the information from the problem. And so now then our equation is negative 1/2 times the change in O3 divided by the change in time equals 1/3 times 6.0 times 10 to the negative 5 molar per second, right? So now all you have to do is solve for this, which is the rate of disappearance of O3. So, easy as pie. All you have to do is divide both sides by 1/2. Essentially, that turns into negative, or the loss in, or the disappearance in O3. All those mean the same thing, of course. Over time, change in time equals 2/3 times 6.0 times 10 to the negative 5 molar per second. And then we'll work that out, and then the answer becomes 4.0 times 10 to the negative 5th molar per second. And again, it's positive because the rate is positive here, right? The rate is positive. Let's move on to the next question. The next one's pretty easy. It says, consider the reaction of A plus B makes C, okay, for which, oops, I'm sorry, I didn't mean to zoom out there. Let me zoom back in. Here we go. So consider the reaction of A plus B makes C. And the rate here, then, the rate law that it gives us is this rate law right here, rate equals K times A, B to the second, okay? Each of these boxes represents a reaction mixture in which A is shown as red spheres and B is shown as purple ones. So rank these in order of increasing reaction, rate of reaction, which is really easy because remember the A here and the B here, right, of the rate law just mean concentration or number of something, number of moles or something, right? And so for box one, all you have to do is say, oops, I didn't mean to put an equal sign there because that's going to get confusing. Let me erase that. If I can get the eraser working, there it goes. What that means then is for box one, right? The rate equals K times how many A's are there? A's are the red circles, right? 1, 2, 3, 4, 5. So we'll put a 5 there, okay? And then B are the blue boxes, or the purple ones, the purple circles. 1, 2, 3, 4, 5. So that's K times 5 to the second for B, right? Because B is a second order reaction, right? With the reaction is second order with respect to B. Cool. Okay, so we'll do that. Excuse me. When we do that, we get 125K, right? Let's do box 2 now. The rate equals K, and then how many red ones? 1, 2, 3, 4, 5, 6, 7 red ones for A, right? B is the purple ones. How many of those? 1, 2, and 3. 3 squared. If we do that math, we end up with 63K, right? And again, so there's the rate constant's the same, so we don't really need to solve for the rate constant. We just care about the numbers that are coming from the concentrations in the stoichiometry, right? So don't even worry about trying to solve for the rate constant. That's why we just left the K there, left it alone without trying to solve for it at all. So box 3 rate equals K times only 3 red balls and probably 7. 1, 2, 3, 4, 5, 6, 7. Yep, 7 purple balls squared. And you work out that math, and you end up getting 407K. So now you can just rank them by fastest to slowest, right? The biggest number, of course, is the fastest. So that's going to be 1 here. The second biggest number is the middle one. So that's going to be 2 there. And the slowest will be this one, which has the lowest number, 3 there. So it's as simple as that. Next question. So the initial rate of the reaction of A plus B to C was measured for 3 different reactions with different starting concentrations of A and B. The results were low with their initial rates, right? Using the data, determine number one, the first thing, A, the rate law for the reaction, B, the rate constant for the reaction, and then C, the rate of the reaction with these two values right here, with these two concentrations of concentration of A and concentration of B. Well, during discussion, we went through all the math, right, to figure out what the reaction orders would be um, for our reaction here, right? And so we start out by saying that. Remember that we start by saying that that K, not K. I apologize. Actually, here I'll just write it over here. The rate equals. I messed up again. Sorry, trying to erase. Sometimes the erase doesn't work as well. You have to hit it really hard to get it to work. There we go. There we go. Rate, except it didn't work. There we go. We know then that the rate equals K times concentration of A. I don't like that I be kind of parentheses there. It should be a bracket. A, right? And then to the, we'll just use M before, like we did in lecture or discussion, times the concentration of B to the N, right? And so we basically have the rate law here already. We just need to figure out what the exponents are. because the exponents are the rate are the reaction orders, right? Those are the reaction orders. How do we figure out what the reaction orders are? Well, in lecture or discussion, I went through mathematically how you can solve for those exponents, right? But when it comes to actually doing this on a test or on some homework, I really want you to do what the trick I taught you, which is the fact that when we look at reaction 1 and reaction 2, where A stayed the same and B was doubled, and then the reaction rate stayed the same, when a reaction rate stays the same and the concentration of one of the reactants was doubled, that means that's a zeroth order reaction, right? That means that's a zeroth order reaction with these two being involved. Okay. Again, the concentration of A remained constant at 0.1 and 0.1 between 1 and 2, but the concentration of B was doubled. And after doubling the concentration of B, there was no effect at all on the rate. That means that was zeroth order. But when you look at the reaction between 1 and 3, here we actually double the concentration of A, leave B a constant concentration, and we get quadruple the rate, right? So with the quadruple of the rate, we know then that this is going to be a second order reaction. That's great because now we know what the rate law is. Because now that we know that with respect to B, it's a zeroth order. With respect to A, it's a second order. We can rewrite this to include our determined exponents. So that would be the rate equals K times A, and the exponent for A would be 2, right? Because when you double the concentration of A, you get a second order reaction because it quadrupled. And then with respect to B, it's actually zeroth order because nothing happens when you double the B concentration. What makes it even easier is that whenever you take any number, right, and you set it so that it's raised to the 0, it actually becomes 1. So you don't even have to draw that. You don't even have to write that anymore. So really now our rate equation or rate law is rate equals K times the concentration of A to the second. We don't have to worry about B anymore. In this particular reaction, uh, the rate is independent of B, right? It's independent of B. It doesn't need to worry about what B's concentration is, okay? Which is good. And again, in discussion, I did go through all the laborious math on how we can actually solve for these two exponents, right? This exponent and this exponent. But really, using the trick I taught you, we don't have to because you can just look at the rates and see if the rates are doubling or quadrupling or staying the same, and you can determine from that if it is a second order or first order or zeroth order reaction with respect to the reactant that is being doubled or not being doubled, right, or being held constant. So I'm not going to ask you on a test to actually do the math. All I will expect you to do is to do this using the trick to figure out whether or not it's a zeroth order, first order, or second order reaction. Just use the rates and see if they double, see if they stay the same, see if they quadruple, and from that, tell me, right, whether or not it's a zeroth, first order, second order reaction. Don't go through all the long math. That's just a waste of time. I just did that in lecture / discussion so that you could see that the trick does work. Okay, so that's A right there. It's great. Answering A was pretty easy. Okay, let's do B then. Now that we know what the rate law is, which is the rate equals K times A squared, or to the second, for a second order reaction, we can then rearrange this now to say K equals the rate divided by the concentration of A squared. Good, because now if we plug in any rate and any concentration the concentration that corresponds to that rate, we should be able to solve for the rate constant, which is what B is asking for. B in this question is asking for the rate constant. So I just picked the first one. So I'll go K equals 4.0 times 10 to the negative 5 molar per second, all divided by the concentration for that rate, which was 0.00 molar for for A. And we do that division, and then we figure out then that the rate constant is 4 times 4.0 times 10 to the negative 3. And the unit there for that one will be meters reciprocal seconds reciprocal. Reciprocal seconds reciprocal sorry, not meters, molar. So that was pretty easy. So now, knowing that we have the equilibrium, not the equilibrium, sorry, the rate constant, right? This is the rate constant. C asks for what is the rate then when the reaction has 0.05 molar A and zero point 0.1 molar B. Well, the great news about this is we don't even care about this because we don't even care about B because B is independent of the rate is independent of B's concentration. So all we care about is this number here. Okay, so we can use our rate law again. So here's C, right? And our rate law says rate equals the rate constant times the concentration of A squared. All you have to do is plug in the rate constant that you just calculated right there, and then plug in the concentration of A right there, right? That's asked above right here, the 0.05, right? And so just don't forget to square it because some people always forget to square it. And so that means then the rate equals 4.0 times 10 to the negative 3 reciprocal seconds, or per mole per second, times 0.050 squared. Oh, molar squared. And that will give you the rate at a concentration of A of 0.05. Let me calculate that real quick. Zero point zero 0.05 squared times 4.0 times 10 to the negative 3. And my answer is, in scientific notation, 1.0 times 10 to the negative 5 meters. I keep on saying meters, I apologize. Molar per second, right? Molar per second. Good stuff. Let's go to the next one now. The next question, it says the decomposition of an insecticide in water at 12 degrees Celsius follows a first order kinetics, right? What does that mean? That means when the doubling of a concentration will double the rate, right? With a rate constant of 1.45 per year. Wow. They gave us the rate constant already. That's great. A quantity of this insecticide is washed into a lake on June 1st, leading to the concentration of 5.0 times 10 to the negative 7 grams per milliliter or grams per cubic centimeter. If you assume that the temperature of the lake is constant so that there's no temperature effect on the reaction, what A asks, what is the concentration of the insecticide on June 1st of the following year? And then B asks, how long will it take for the insecticide concentration to decrease to 3.0 times 10 to the negative 7 grams per cubic centimeter? Okay, so we're given everything we need here. The first thing to notice is that it says it's a first order reaction, right? And so whenever it says it's a first order reaction, we know what that means when it comes to rate, but we also need to remember that what this means is that we're going to be using the first order integral rate law, right? The first order integral rate law, uh, where the ln of a concentration, right, versus time will be a straight line, right? And so that equation for a first order reaction, if you recall from the your welcome chart I gave you, is ln a at time t equals the negative k at the time plus the natural log, or the ln, of the initial concentration of A, right? The zero is initial. So this is pretty simple. Given the information from the problem, we can just plug and chug, like you always say. So the ln, or the natural log of the insecticide, right, at time 1 year equals everything that you plug in here, which is the negative, right? And the k right here is given to you here at 1.45, okay, per year. That is multiplied by the duration, or the time, the t. It's telling you here for the following year, so that's 1 year. And that's then added to, right here, by the natural log of the initial concentration, which is given you right here. Grams per cubic centimeters. Okay? And so, what that means then is that all you have to do is carry out this math right here, and it will give you, right, the insecticide concentration after a year. Okay? And so let's carry out the math. I need to move up a little bit here, running out of room. So the ln of the insecticide at time 1 year equals, again, negative 1.45 or 1.45, which is times 1, which is just the same number again for the 1 year, plus negative 14.51. That's the number you get when you take the natural log of 5.0 times 10 to the negative 7. Okay? And then we carry out that arithmetic, and the number is now negative 15.96. Okay? So the question now remains, how do you get rid of a natural log when you have to have a natural log of some variable that you're trying to solve for? Well, the opposite of a natural log is actually the the e to that number, right? It's the e to that number. So ln, or the natural log of the insecticide at time 1 year equals e to that number that we got from over here, negative 15.96, right? E to that number. So basically I took an e on both sides, right? I did an e to both sides, okay? And so when you do an e to both sides, you can cancel out the ln's there, so you're left with insecticide, and then at time 1 year equals e to the um, negative 15.96, right? And so E is a calculator in your E is a calculator. You use a function on your calculator. It's under the log button. You have to press second and then ln. So it's actually the natural log button, but the second function, the natural log button. So press second and then natural log, and that gives you e to the x. And when you do e to the x, or e to the negative 15.96, your answer is 1.2 times 10 to the negative 7 grams per centimeter, per cubic centimeter, right? Or mil, because cubic centimeters and milliliters are the same. Okay? And that's your answer for this one. At 1 year, the concentration of the insecticide will be 1.2 times 10 to the negative 7 grams per cubic centimeter. And that's how you answer A. Okay? So let's do B now. B says, it asks, how long will it take for the insecticide to get to concentration of 3.0 times 10 to the negative 7 grams per cubic centimeter, right? Again, this is easy because all you have to do is plug in the numbers that they've given you, right? Using the same equation as you did before, because again, this is a first order reaction, okay? And so this is the integrated rate law for the first order reaction, right? Don't forget that. Integrated rate law for first order reaction. So you use this rate law, right, or this integrated rate law here for both of them, A and B. So again, plug in what you know. We'll start out by saying ln, or the natural log of the insecticide, right, what we want it to be at some certain time, or whatever we need it to be, which is 3.0 times 10 to the negative 7. We set that then equal to the rest of the equation, right? And when we set that equal to the rest of the equation, it's negative. Again, we have here a rate constant of 1.45 years. So 1.45, right, years, or per year rather. 1.5 per year. And then multiply that by t. And in this case, we're going to be solving for t. Why are we solving for t? Because it asks us how long will it take for us to get to this concentration. Okay? Plus the natural log, right, of the initial concentration, which was the 5.0 times 10 to the negative 7 grams per cubic centimeter. And then we'll close that off. Right? I'm going to move it down just a little bit so I can do this math now. Now this one's pretty easy because all you have to do is solve for t. Right? First thing I would do is subtract from both sides the ln of the initial concentration right there. Subtract from both sides. So what you'll end up with then is, after you subtract from both sides, right, and then you'll divide both sides by that, the 1.4, you end up with this. t equals the natural log of 3.0 times 10 to the negative 7 minus the natural log of 5.0 times 10 to the negative 7 grams per centimeter cubed, which we're doing the math now, so we don't really need to put that in there. Okay? All that is divided by what? The 1.45 of the rate constant. Sorry, I got a little messy there. And I'm trying to erase it, it won't let me. 1.45, right? The 1.45. See, from here. We'll do that math, right? Take the natural log of the 3.0 times 10 to the negative 7, subtract from it the natural log of 5.0 times 10 to the negative 7, and then divide it by 1.45, and then that tells us that it takes 0.35 years, or year, because it's less than 1, all right? So 0.35 of a year to be able to get you to a concentration of 3.0 times 10 to the negative 7 from the initial concentration of 5.0 times 10 to the negative 7 of the insecticide, right? That's simple. That's simple. All right, so let's do the very last one now. Here you have a set of data, right? And all you have is time and concentration, okay? The concentration of nitrite, okay? It's asking the data were obtained below from a gas phase decomposition of nitrogen dioxide at 300 degrees Celsius, right? And here's your chemical equation right here. Not even balanced, but it might not even matter for this equation, for this particular problem, because we're already given this here, which is the reactant, okay? And it's asking you, based on this information right here, is this reaction first order or second order with respect to nitrogen dioxide? Okay, nitrogen dioxide. I might have said nitrite earlier. I meant to say nitrogen dioxide. I apologize. Anyway, how do we tell? Well, remember that you can tell the difference between a first order reaction and a second order reaction, because in a first order reaction, if you take the natural log of the concentration of the reactant and plot it versus time, then the line will be straight. Okay, but if you take the 1 over the concentration of the reactant and plot that versus time and it's straight, then it's a second order reaction. Okay, so what does that mean? That means you're going to have to plot some stuff, right? So the first thing to do, or calculate some stuff and plot it. So the first thing I would do is I would check to see if it's a first order reaction. Okay, so here's how we do it. I'll make another column here, and the column will be ln and O2. Okay, and then I'll go through and take the natural log of 0.01, and that turns out to be negative 4.605. If I take the natural log of 0.00787, I get negative 4.845. If I take the natural log of 0.00649, then I get negative 5.037. If I take the natural log of 0.00481, I get negative 5.337. And then lastly, if I take the natural log of 0.0038, I get negative 5.573. Okay? So now that I have that, I need to graph it, right? I need to graph it. So I'll graph it down here. Let me move it, get some space here. Okay? Here's my graph. And I put time here. And I'll start out at 0, of course, time 0. And here, here, and here will be time 100, time 200, time 300. And you might be asking yourself, asking me or yourself why I picked those times. That's because those times are given right there. All right. You can put the 50 in there if you want to, too. Okay, if you want to. I'll put the 50 in there just because it's in there. Okay, 50. And then over here on the y-axis is going to be the natural log of the concentration of nitrogen dioxide. Okay, and my highest number is 5.5, so I'll start out with 5.5 here, negative 5.5 rather. So I'll start out with negative 5.6 there, right? And I'll just go up in negative 0.2 increments, right? So negative 0.454, negative 0.52, negative, and I ran out of room there because of my title, but 0.50, right? Negative 0.4, negative 4.8, and then my last one right here will be negative 4.6. Okay, and I'm doing that because the last one, the highest number I have here is negative 4.6, right? Sorry, I missed this. I think I said point something. Let me say that again. It should be negative 5.6, negative 5.4, negative 5.2, negative 5.0, negative 4.8, negative 4.6. And I'm literally just going upwards by negative 2s and negative 2 increments, okay? And so now I'll plot it all, right? So at time 0, right here, I had a number of negative 0.065. Negative 4.605. So here's time 0 right here, right? Like that's where the 0 is at. And then negative 4.6 is right there, right? So I'll put a dot right there. Okay, pretty close to the 4.6. I mean, not exactly on it, but pretty close. Okay. My next time slot here is 50. So 50 at 50, I have negative 4.845. So here's 50 right there. And negative 4.845 is right about thereabouts, right? Just below. And then at 100, I have 5.37. So very close to 5.0. Okay, very close to 5.0. And then at 200, I have 5.3, which is between 5.2, negative 5.2, and negative 5.4. And then at 300, I have a negative 5.5, basically right about there. And then I'll connect the dots, like so. You can see that the line is not straight, right? The line is slightly curved. And if it's curved, that means that it is not a first order reaction. Not a first order reaction. I'm sorry it looks so messy here, but it's hard to draw, a nice looking graph using an iPad and stuff, right? So if it's not a first order reaction, well, the question already gave us only gave us two options: first order or second order. So it must be a second order reaction. But what can we do to confirm that it is indeed a second order reaction? Well, remember that for a second order reaction, you have to take 1 over the concentration of NO2, right? And if that line is straight, when you plot the concentrations versus the times versus the the 1 over the concentrations, then that means that's going to be a second order reaction, right? So let's go through and do our little chart in the math again, right? I do 1 over 0.01, and the number I get is going to be 100. I do 1 over 0.0078, and I get 127. And I do 1 over 0.00649, and I get 154. And then I do 1 over 0.0048, and I get 208. And I do 1 over 0.0038, and I get 263. Well, that's good. That's good. Okay, okay. What does that mean then? What I have to do now is plot the 1 over the concentration values against the time. So I'll draw another graph. Okay. And again, it's going to be simple because I'll just do the same thing I did before. I have time 0, time 50, and then time 100, and then time 200, and then time 300. Right? Not exactly the scale, but close enough. And then over here is really easy too, because let me scroll down and get myself some more room. That's time. Right? Wow, that's really messy. Time. There we go. Over here will be 1 over the NO2 concentration. Okay. And so if I start out with 100 and end it with 263, I can just say, let's start out with 50 down here, and then go up to 150 here, and then go up to 250 here. And that should cover everybody. Okay, that should cover everybody. All right, so at time 0, I had 100. Okay. At time 50, I had 127, which is just below 150. At time 100, I had 154, which is just above 150. Right? And then at time 200, I had 208, which is right there in between. Right? And then at time 300, I had 263, which is all the way up here. So notice how this line is a straight line. And since it's straight, we know then that this is a second order reaction. And that's your answer. Is the reaction between NO2 becoming NO and oxygen first order or second order reaction? It's a second order reaction. How do we know? Because when we plotted the 1 over the NO2s, we get a straight line. Okay. Good stuff. All right. Well, that's all that we have, right? That's all she wrote for this particular worksheet from discussion. If you have any questions, let me know. Send me a message on Teams, and have a good weekend.